And so now in today's class we are going to discuss about potentiometer, the principle of potentiometer and its working and the uses of the potentiometer. And before going to that, let us discuss about one more device briefly here. The device is nothing but rheostat. We already used the rheostat in previous circuits. So rheostat is nothing but it is a device used to control the current, or we can control the potential difference. That means we can apply a desired potential difference we can apply, or we can allow the desired current in that circuit. So we can control the current or potential difference in that circuit. It's nothing but simply a variable resistor. Rheostat is nothing but a variable resistor there. And we know the circuit symbol for this rheostat also. So that means now see here, a rheostat is a device used for varying the strength of current in electrical circuit. So that means it consists of a nichrome wire wounded on some insulating cylinder, halo cylinder. Like here it is chain of clay cylinder, that means like insulator cylinder. So that means the wire is insulated, that means oxidized, means it is insulated from others here. That means even though the wires appears to be in contact with each other, there is no electrically they are insulated from each other. There is no electrical contact between those wires. And so now I will show this diagram for this rheostat here, then you will get a more clarity about that. So let us see the diagram for this. So now see this. This is the diagram for this. That means this is the rheostat here. This practically the rheostat will be looks like that. So this is nothing but what is said here. Here you can observe that the wire is wounded here on this chain of clay cylinder. That means halo some insulating cylinder. The wire is wounded here. There is not a single wire. The wire is wounded for many turns here. And so that then this is the sliding part here. By sliding this, we can vary the resistance of the circuit here. That means one end may be connected here and the other end of this wire may be connected here. Or sometimes you may connect between this terminal and this terminal here. That is our choice. That depends on that given circuit how we are going to use here. And so now as the wires are insulated from each other, even though there is a contact, physical contact between those wires, they are electrically insulated from each other. So that means now we can observe that it can be sliding, this is sliding like this. So that when it is sliding, the resistance is varying here. We can put any desired resistance in that circuit here. So we can put any desired circuit by sliding this knob here. So just if this knob is slided here, then accordingly that resistance will changes here. Resistance in that circuit will changes here. So that means now suppose if you are connecting like this. So if the knob is here and if you are making the connection between this terminal and this terminal, and so then current will flow only this part here. Current will flow only this part. That means here current will flow only this part of the circuit here. That means it enters, for example, here. Then it will flow through this coil here and then it comes out of the circuit like this. Or if you are connecting between these two terminals, current is suppose entering here and leaving here, then it will flow only in this part here. That means by moving this, we can put either maximum resistance we can put or minimum resistance we can put here. So that depends on our requirement there, right? So that is a working of this rheostat here. So that means now let us see how it is used here in that circuit there. And so now this it can be used as I said, it can be used as a current controller, or we can control the potential difference in that circuit. If you want to control that current here, then we need to give the connections like this. If suppose say current is entering here and the current is entering in this circuit like this, then it will leave the circuit here. So that if the connections are given like this, as I said, current will flow only this part of this resistance here. That means there is no current in this part here. This X to B, there is no current here. Only there will be current only from A to X. Then it will flow through this conducting part like this. Or you can also give the connections like this. That means now if suppose a current is entering here, then it will flow only along this path here. Then after that it will come out of the circuit like this. Now in this part AX there is no current here, right? So that means either way you can connect there. So just by moving this sliding contact here, we can adjust the resistance in that circuit. So if you are adjusting the resistance in that circuit, then automatically the current in that circuit will changes there, right? So we can adjust the resistance sliding contact here so that we can put any current in that circuit. So like that we can control the current in that circuit there, right? Now let us see how to control this potential difference here. We can also control the potential difference in this circuit here. So now here if you want to control the potential difference, that means now rheostat has a potential divider here. Then connection should be connected. Connection should be given like this. That means we connect the cell across this rheostat here. We are connecting, observe this, we are connecting this cell across this. In the previous connection, there is no cell across this. Cell will be there in other part of the circuit here. So now the cell is connected here itself. And so now if you are again connecting this circuit, remaining circuit connections are given from A and then other connection is given here. Then potential difference in that circuit is nothing but only this potential difference will be acting as potential difference in that circuit there. So if you want to increase the potential difference or if you want to decrease the potential difference, then we can do some changes. That means by sliding this contact here, we can adjust this potential difference there, right? So that means now if you want to increase the potential difference, we should move towards this B. If you want to decrease the potential difference, we should move towards this D here. That means now this total potential difference will be there. This total potential difference V will be there across this AB here. So just by sliding this contact, either we can increase the potential difference or we can decrease the potential difference, or we can put any desired values in that circuit there, right? And now here let us see this. If suppose if contact is made at some point, actually this is nothing but our circuit symbol here, circuit symbol for the rheostat. So that means whereas variable resistance, if it is only variable resistance, then just we represent like this. This is just variable resistance. Now rheostat means specially it is represented like this. The rheostat symbol is specially represented like this. And here suppose here it is given that if the contact X of the sliding wire S, constant S can be at a distance of 3/4 of the length of the wire AB from the A. The potential difference between A and X will be therefore 3/4 of the total potential difference here. That means now, see here simply what they are saying here is if this length is equal to 3L by 4 here, then this total potential difference V will be there across this total resistance here. Now only if you are taking this length here, then this is nothing but then potential difference across that AX, we can write this as potential difference across this AX. Then this total potential drop per unit length, this total potential difference V is there acting for a length of L here. If suppose if you are taking this L as the length of this wire here, right? If you are taking that as a total length as L, then this total potential difference per unit length, you can write this as V by L into our required length is 3L by 4 here. So then potential difference across that AX, we can write it as 3V by 4. So 3/4 of this total potential difference will be there in that given circuit there. So now here in potentiometer, this part is very important here. This actually we call it as, here you can observe that this is nothing but potential drop per unit length. If you are taking this, V is the total potential difference across this length L, then potential drop per unit length is called potential gradient, right? So this V by L is nothing but our potential gradient here. So like we defined velocity gradient in viscosity while discussing viscosity, and in fluids we also discuss like pressure gradient. So pressure gradient or velocity gradient means rate of change of velocity with the distance, and similarly pressure gradient means rate of change of pressure with the distance. So here similarly here it is the rate of change of this potential difference with the distance. So that means the potential gradient means potential drop per unit length. So that is called potential gradient here. Into this, across which we need to find this length, that length we need to multiply here. So potential gradient into the length of that part will give the potential difference across that part, given part here. So that is a important thing regarding this. And now next, before going to that working principle of this potentiometer, and let us see one problem here. Then that problem is useful in the discussing that potentiometer there. So let us see this now, this problem here. So this problem is nothing but here the circuit shown in the figure, the galvanometer shows a zero deflection if the batteries A and B has negligible internal resistance, the value of R is. So this resistance value they are asking here. So you can observe that is a previous mains question. So then here the galvanometer shows a zero reading. So that is the important point here which is useful for us in the discussion of this potentiometer. So galvanometer shows zero reading means here, then when the galvanometer shows zero reading means the potential difference across this resistance. Galvanometer shows zero reading means basically there is no current flowing here. That means current flowing in this path will be equal to zero. No current is flowing here, right? So when there is no current, even though circuit is closed, the circuit is a closed circuit, right? But there is no current flowing to that. So when that current flowing to the circuit will be zero means the potential difference across this resistance must be equal to the EMF of the cell. So if these two ends are at the same potential, that means here suppose if this end is grounded here, this end is grounded, let us consider here, then this is at 2 volts. Then if this end is also at 2 volts, then there is no current flowing between those 2 points here, because both are at the same potential here. Then this is also at 0 volts, right? And so that is the condition there. So when the galvanometer indicates 0 reading, the potential difference across this resistance must be equal to the EMF of the cell connected across this, right? And so that means here you can consider this potential difference as 2 volts here, right? So here potential difference across this resistance is 2 volts. Now in this circuit, if you consider here, that means now this circuit if you consider, in this closed loop, left loop, in this loop if you consider, total we are applying at 12 volts. Out of the 2 volts potential difference is there here. The remaining 10 volts must be there here, right? So 10 volts potential difference must be there here. So then as you know the potential total, so that this potential difference will be equal to this total applied potential difference here. There is no current flowing in the circuit here, so that this value is equal to directly 2 volts we are saying. Now as we know the potential difference and resistance for this 500 ohms, we can define the current flowing in that path there. Therefore this current we can write this as V by R, so it is 10 by 50 we can write, 500 we can write. So which is 1 by 50 amperes. Right, that is the current flowing through this path here. And as there is no current in the galvanometer, the total 1 by 50 ampere should flow through this resistance only, right? So in that resistance, you know the potential difference 2 volts and the current 1 by 50 ampere. So from this we can calculate the resistance for that. So that the resistance we can write this as so resistance is equal to like V by I we can write there. So there that V is nothing but 2 and this I value is 1 by 50. So that you will get that value as 100 ohms, right? So that is the 100 ohms is the potential difference. 100 ohms is the resistance of that resistor there, right? So that means that is the resistance of that unknown resistance there. So here the important thing which is useful for our potentiometer discussion is when this galvanometer shows 0 reading, the potential difference across this resistance must be equal to the EMF of the cell. So this principle, remember this principle we will discuss in, we will use in principle of while discussing the principle of potentiometer, right? And so now the experimental setup and this potentiometer I can show here, then I will show an animated video also based on this. So first let us simply show what is this potentiometer and what are the uses of this potentiometer here. So potentiometer is basically it is a device used to measure the EMF of a cell, or we can compare the EMF of 2 cells, or we can find the EMF of this unknown cell. Unknown cell we can find, and we can find the potential difference between any 2 points in that circuit, and we can find the internal resistance of a cell, and we can find any EMF, thermo EMF produced in that circuit. Thermo EMF means we will discuss later. And it is used to calibrate many devices like voltmeter. And mainly the main advantage of this potentiometer is it gives more accurate value when compared to voltmeter. So we already discussed about the voltmeter. Voltmeter is also used to measure the potential difference between any 2 points there. But the disadvantage of this voltmeter is practically we discussed that practically the voltmeter, how the resistance of voltmeter and what is the resistance of ideal voltmeter. The resistance of ideal voltmeter is infinite, and practically we say it possesses a very high resistance there. So but practically that means no voltmeter is having such a infinite resistance there, right? And so any voltmeter, any practical voltmeter does not give the accurate values. We mentioned already any device while discussing about voltmeter and ammeter, any device like ammeter or voltmeter will measure the value less than the accurate value, right? So then that we discussed already, and we solved some problems based on that percentage calculations also, percentage error in the measurement of that voltmeter. So that means that is the disadvantage here. When it is having some finite resistance, what will happen is the voltmeter will draw some current from the main circuit. So when it is drawing from the current from the main circuit, automatically the current in the circuit will decrease or it will change, and automatically the potential difference between them also changes there. Between which points we need to find potential difference between those points also changes. So that is a disadvantage of this voltmeter. and that can be overcome by using this potentiometer here. So that is, a potentiometer does not draw any current from the main circuit. That's the main advantage of this potentiometer, and so we can say it gives more accurate values when compared to that of voltmeter. Even though other device voltmeter is there, this potentiometer will give some more accurate values when compared to that of voltmeter here. So this potentiometer generally consists of 10 meters wire. This is here generally in a simple circuit we are showing it as a single wire here. That AB is a single wire we are showing here, either here or here. You can observe that it is not actually such a single wire here. So that means it's generally AB wire. In case of meter bits, we mention it is of length 1 meter only, but here generally it will be of 10 meters length, or sometimes 400 meters, 400 centimeters will be there, or sometimes it will be 6 meters will be there. So like very long when compared to that of meter bits. So for that reason, if you are arranging a single wire like this, if suppose 10 meters wire we are taking in that experiment, and if you are arranging that a single straight wire 10 meters wire like this, then the operator size will become too big. And so to reduce the size, what we will do is, I will show you practically there. So we will take a 1 meter length, so that they are arranged side by side, so that the size of the operators will be reduced there. So then in this series, generally we take this value as EMF of the cell as E here. So then this is the first part of the circuit is called primary circuit here. So this part of the circuit is called primary circuit. So it consists of a cell of EMF E and internal resistance R, and this is the key here. And here this series resistance or rheostat resistance RH, or sometimes it is represented with RS. There is no importance for the symbols there. So some resistance will be there. So either RH or RS you can represent there. And this is the potentiometer wire. So as we discussed in the meter bit, this wire is also made up of the materials like constantan or manganese, because of the same reason, because their alpha is very small. For constantan or manganese, the alpha value is very small, and so that their resistance does not change by the large amount due to the variation of the temperatures. So because of that reason, that value such a materials we use here. So this part of the circuit is called primary circuit. So it consists of a cell and resistance and a key, and this is nothing but our potentiometer wire. AB is nothing but our potentiometer wire. It is having some length, say capital L, generally we represent, and some resistance R. So that means this L is taken as the length of this wire, capital L, and R is taken as the resistance of this wire here. And now this remaining part, this part is called secondary circuit here. So here it consists of a cell whose EMF is to be determined. We need to find this EMF of the cell. It is connected in series with this galvanometer and this jockey. And about this jockey we saw already in the meter bit experiment. And this in general with the galvanometer we connect some resistance, high resistance in series, or we use the short circuit method to control this, to protect this galvanometer here, right? So this principle of this, this is a circuit diagram, about the circuit diagram of this potentiometer. And so now here one terminal of this another cell, see this some important points regarding the circuit here. The specific resistance of potentiometer wire must be high, and its temperature coefficient must be low. So that is why we are using the materials like constantan or manganese. About this, the specific resistance of this material must be very high. That means it should have some high resistance, but its alpha value, temperature coefficient, should be very low. And higher potential points of the primary and secondary circuits points must be put together, and the lower potential points must be connected to the jockey. So this is the circuit here. That means while giving this potentiometer circuit, these are some important precautions you should note here. The positive terminals of both the cells must be connected to the same point here. By mistake, if you connect the reverse, then you never get a null point here. That means zero deflection in the galvanometer. So positive terminal of this primary cell, that means cell in the primary circuit, and a positive terminal of the cell in the secondary circuit, both must be connected to the common point here. And this lower potential is connected to this jockey. That is another point here. The value of unknown potential difference must be greater than that of value of known potential difference must be greater than that of value of unknown potential difference to be measured. So this is another important condition to use the potentiometer here. Here potential, the EMF of the cell, this is the EMF of the cell to be measured, or the EMF of the unknown cell. This potential difference must be less than that of potential difference of that means less than that of EMF of the cell used in the primary circuit here. So what actually means is the EMF of the cell must be less than that of potential difference across this AB here. That is the actual proper condition here in general. In general, we will express like this. Here I can make this conclusion as the potential difference across this AB must be greater than that of EMF of the cell to be measured here. That only we are expressing like this. We are saying in terms of this EMF of the cell in the primary circuits. Actually, this is the proper condition or must and should condition here. So if this condition is not satisfied, you never get a balancing point by using this potentiometer here. The potential gradient must remains constant. For this, current in the primary circuit must remains constant, and the jockey must not be slide on the while the contact with the wire. So this is the potential gradient. So we will define now potential gradient, which we defined previously, the rheostat potential difference per unit length. So that potential difference must be constant throughout the experiment. So throughout the experiment, we should maintain the constant potential difference, and that is possible when constant current is flowing through this primary circuit here. And then next, the sliding, we know jockey can be pressed at different points here while checking for the zero deflection, but it should not be dragged along this. So this point we discussed already in the meter base. So because if you are dragging on this, then what will happen is the deformation of the wire may take place. Because of that change in the area of cross section, there may be changes in the resistance of that wire there, so that the values will be different at the different times you will get there. The diameter of the potentiometer wire must be uniform everywhere. That means here the resistance, again we take like R is proportional to L, generally we consider here. So because of that reason, here this potentiometer should have the common area, uniform area of cross section here, right? So then let us see about this potential gradient. So for this potential gradient, we need to consider this circuit here. So in this circuit, the current flowing in the primary circuit, we can write this as current flowing in the primary circuit. So this is our primary circuit here. So current flowing in the primary circuit, you need to write there. And now see this potential gradient calculation here. As I said, this potential gradient calculation is very important in potentiometer here. So potential fall for unit length is called potential gradient. So x is equal to, we are representing some x, there is no any specific symbol for this. You can represent either with x or lambda, or you can sometimes you may represent some v or v by rho. So you can use some different symbol. There is no any specific symbol for this. So here we are taking it as x. So x is equal to v by L. So then where v is potential difference across this wire AB here. Then potential difference across this wire AB, we can write this as, if suppose I is the current flowing through this wire here, so then V is equal to IR we can write, where this I is the current flowing in this. So current flowing in the primary circuit, when galvanometer indicates a zero reading here. So that means in that case, when null deflection is there, then current will flow only in this circuit here. Here current is high and here also current is high. This galvanometer indicates zero reading here. So in that case, we are writing this expression now. So then current flowing in this primary circuit we can write as total EMF by total resistance we can write. So then E by total resistance, in the sense this R is nothing but resistance of this wire, total resistance AB, and L is its length here. So then this is E by R plus RH, series resistance or rheostat resistance here. And this is E, that R, smaller internal resistance. So this is the total current expression. So current into this I we can write here, that means R we can write here, resistance, IR formula. Now our potential gradient is nothing but x is equal to V by L. So potential gradient, potential drop per unit length. So just we need to, here we need to divide with this length here. So you can observe this now, potential gradient depends on that resistance per unit length, the resistance per unit length of this bridge wire, that means this potentiometer wire, AB wire, and then radius of the potentiometer wire. That means this resistance means you can say that it depends on the radius of this potentiometer wire here. And then specific resistance of the material used for this. That means this resistance, that is nothing but depends on the resistance there. R is equal to rho L by A formula you can write. By using that we are saying here. So it depends on resistance per unit length or potentiometer area, that means radius, and specific resistance, and current flowing in this wire here. How much current is flowing in this? and then it indirectly depends on these two values. That means current flowing in there. That means actually basing on this expression, first we are saying these 3 points here. Now this I expression we can write like this. So that means from this what we can say is indirectly depends on this, how much EMF is there in this and how much series resistance is connected here. Series resistance or the rheostat resistance there. So there is a calculation of this potential gradient there. Now the principle of this potentiometer, now I can write this as, now say this principle of this potentiometer here. So the principle of this potentiometer means now we press the jockey at different points here. After making that, our actual procedure is nothing but after making these connections like this, then we press the jockeys at the different points, that means at the ends A and B, and we observe the deflections in this galvanometer. The galvanometer should indicate the deflections in opposite directions like our meter bits. So then connections are correct, then we can proceed further taking the readings here. So otherwise we need to check these connections again. Any loose contacts may be there or any wrong connections may be there. So then we press the jockey at the different points here. Suppose now we are getting this null deflection at the point J, when the jockey is at the point J, and then L is this length distance between A and J here. That means now let us come to the problem which we discussed previously there. Now the galvanometer, this J1 and J2 are indicated. I will explain them later. So first let us discuss this. At the point J, this galvanometer, when the contact is jockey is made at the contact at the point J, galvanometer indicates 0 reading. So now when the galvanometer indicates 0 reading means, now let us come to the problem previously what we discussed here. So that means when this galvanometer indicates 0 reading means that EMF of the cell must be equal to potential difference across its resistance, right? So now we need to apply the same principle here. So we need to apply the same principle here. When galvanometer indicates 0, the EMF of the cell must be equal to the potential difference between this A and J. So right, potential difference across this AJ must be equal to EMF of the cell. So that means now we are writing that point only here. The EMF of the cell will be equal to potential difference across this. Then how to write the potential difference across means potential drop per unit length. We already mentioned that potential drop per unit length. So into this length L we need to write here. So potential drop per unit length means suppose here this potential drop per 1 centimeter is like, suppose I am giving like 2 volts per centimeter if it is, for example. Now suppose if you want to measure the potential difference across this 5 centimeters length, if you want to find, if this is 5 centimeters here, then potential drop must be equal to this 2 into 5, and so that you will get that as 10 volts. So 10 volts is the, if for 1 centimeter if 2 volts potential difference is there, then for 5 centimeters the potential difference is nothing but 10 volts. So like that we need to write here. So for 1 centimeter it is X we are taking here, potential drop per unit length as X. Then for L centimeters we are writing here. So potential difference between A and J must be equal to X into L, right? And so that must be equal to the EMF of the cell here. So we are equating that E is equal to X into L. And you can substitute that X value by using our previous potential gradient expression. Then this is the EMF of the cell here. And so now from this EMF of the cell you can observe that all these are constant values here. This all belongs to the primary circuit, right? Except this small L, you can observe that remaining everything in this expression is depends on the primary circuit. Now if you want to measure the EMF of the cell in the secondary circuit, that means we need to connect the different cells in the secondary circuit. So if you are changing the cell in the secondary circuit, it doesn't affect any value in the primary circuit. So from this what we can conclude is, except this L, remaining all are constants. So EMF of the cell to be measured is directly proportional to length here. So this is nothing but we call principle of potentiometer here. That means if you are taking a cell of EMF E, if you are getting 10 centimeters. If you are taking a cell of EMF 2E, then you will get a balancing length of 20 centimeters, right? So that means if EMF is increasing, then automatically balancing length also increases here. So that is nothing but we call the principle of potentiometer. And now let us come to this connection set, contacts at the J1 and J2. So at the J, it is indicating that zero deflection here. Zero deflection is what we are concluding is potential difference across this AJ must be equal to EMF of the cell. Now when J is, if you are making the contact at the J1 here, then the J1 means then here length of this wire, potentiometer wire is decreasing here. It is less than L. And so automatically the EMF across it, that means potential difference across this will be less than this EMF here. When it is less than this EMF, then this is the case here. Current flows through the galvanometer in opposite direction. That means now here current flows in the circuit like this. It will flow, current will flow like this. That means now this EMF will dominate in that case. So then current will flow through this galvanometer like this. If the jockey is made at the contact at the point J, if the jockey is J2, if the contact is made on the right side of this balancing point, then EMF potential difference across this AJ2 will be greater than that of EMF of the cell. Then current will flow in opposite direction. So that is nothing but what I mentioned here. If V is greater than E, then current will flow in the galvanometer in one direction as shown. So if it is flowing in one direction, if E is less than, if you are making the contact here, then current in the galvanometer will be in opposite direction. So if V is equal to V, then no current flows through the galvanometer. So that is nothing but our balancing length or the balancing point we call here, or null method. This is nothing but we also call it as null deflection or null method. So zero, null means it is nothing but zero. So that means when it is made at Z, no current flows through that. If you are making it J1 or J2, some current will flow but in opposite direction here. So that there will be some current across this, current is flowing through the cell in the secondary circuit also here. So when you are making it the contact at the J1, no current is flowing through this galvanometer. No current is flowing through the galvanometer means then no current is flowing through the cell actually. When no current is flowing through the cell, then we the potential difference across the cell is nothing but EMF of the cell here. So that we can measure the EMF of the cell by using this potentiometer. Whereas it is not possible by using this voltmeter, because by using this voltmeter, if you connect a voltmeter across this, the voltmeter does not have infinite resistance, so that some current will flow through the cell here. When current is flowing through the cell, we know potential difference across the terminals will be E minus IR we need to write, terminal voltage. We discussed already in the cells. So E minus IR we need to write here. When you are writing E minus IR, then it will be automatically less than that of EMF of the cell. You can't measure the EMF by using this voltmeter, practical voltmeter. So whereas by using this potentiometer, now we are measuring this EMF here. No current is flowing through the circuit here. That is the advantage of this potentiometer when compared to that of voltmeter, right? And so now let us see this some principle here. The practical potentiometer and its principle, how to find this principle. I will show that animation regarding this. Now see this potentiometer here. So as I said, this potentiometer will consist of like 1 meter length wire connected like this. So actually it consists of the wire like this. So you can observe that these different 1 meter wires are connected like this. And they are connected, joined at the ends like this, so that all those are in series here. All those wires will be connected in series here. So right. So that means now this is of length 1 meter. This wire is of length 1 meter, and all those are connected. That means these two are connected here like this, and these two are connected here like this. So like that, the ends to ends connected, so that this total wire is in series here. So right. So that is a generally it may be 10 wires. They are connected here at the ends by using these copper strips. These are nothing but copper strips here. And this is the meter scale is fixed here beside this wire, so that we can measure the balancing length here. Balancing length can be measured easily with the help of this meter scale. Now see the principle of this potentiometer here. So we are taking some battery, as we discussed. We are going to describe the primary circuit now. Let us see this primary circuit. So this is a battery in the primary circuit here, which provides a constant EMF. And then this is the potentiometer wire AB, and then this is a plug key here, and then battery is connected here. So here it is not shown that like what we call rheostat or variable resistance, or it may be there, or it may be in some circuits, it may not be there. In numericals also sometimes they won't mention about this series resistance or the rheostat here. So here also that rheostat is not shown. It may be there. Practically, if you are doing the experiment, generally we connect that rheostat also, some resistance, or rheostat or some resistance is also connected there. So now this is nothing but current flowing in the primary circuit. So even if current, the secondary circuit is not there, then this current will flow to the circuit here. So this is called primary circuit. So these are primary circuit connections. And next, then a cell whose EMF is to be determined is connected like this. So here you can observe that the positive terminal of the cell is connected to the positive point, where this positive terminal of this cell in the primary circuit are connected here. So both the positives are connected to this common point here. And there is a galvanometer and there is a jockey here. So now this part is nothing but we call the secondary circuit in that potentiometer. So then here we press the jockey at point C and point B here until the galvanometer shows a zero reading. At point A and at point B means the deflections will be in opposite directions. Then if the connections are correct, then we proceed for taking the readings, or otherwise we check the connections again. There may be any wrong connections in that circuit there. And then we press the jockey at the different points so that it shows some zero deflection here. So then suppose we are making this contact at the point A so that it indicates a zero reading here. So then it indicates zero reading means now we can observe that there will be current flowing in the primary circuit here. There is still some current is flowing in the primary circuit here, but only the current in this secondary circuit will be zero. There is no current flowing here, right? And so now this length is nothing but this AJ length is nothing but our balancing length here, where the galvanometer indicates a zero reading. That length is nothing but balancing length small l. Now the potential difference across that we can write it as potential difference across this AJ we are writing here. So that means IR into L we are taking here. That I is nothing but current flowing in the primary circuit, and here they are taking this R as the like resistance per unit length of the wire here. So that this value will represent, IR value will represent potential gradient here. So the potential gradient is shown by IR into this balancing length. So that is a potential difference across this. So then we know potential as the galvanometer indicates zero reading, potential difference across this must be equal to the EMF of this cell here. So even though galvanometer indicates zero reading, you should observe that still current will flow through the primary circuit here. This current will flow through the primary circuit. Now this potential difference across this AJ must be equal to the EMF of the cell. Only current is not there in the secondary circuit here. So then we can equate this EMF and the potential difference there. And so that this is our circuit here. Since this I and R are constant, then we can write this E is proportional to this length. So this is nothing but our principle of this potentiometer here. So hence EMF of the cell is directly proportional to the balancing length. So this is called the principle of this potentiometer. Got it? This is a circuit regarding this potentiometer here, or principle of this potentiometer, or EMF of the cell also can be found like this only. So that means just by pressing the jockey at different points we find the L value, balancing length. So from that we can calculate this EMF of the cell here, and you can also compare the EMF of the two cells. So right. Next, about this sensitivity of this potentiometer. The potentiometer is generally said to be more sensitive if it is measures a small potential difference more accurately. That means if it is measuring small potential difference, if you are comparing two potentiometers, for example, say first potentiometer can measure up to 1 volt, whereas second potentiometer can measure up to 0.1 volt. Then the second potentiometer is said to be more sensitive when compared to that of first potentiometer. So that means if it is measuring a smallest values, then it is said to be more sensitive there. So then actually the sensitivity of the potentiometer can be dependent on that potential gradient. So potential gradient is nothing but potential drop per unit length. So potential sensitivity is inversely proportional to the potential gradient there. Because potential gradient is nothing but potential drop per unit length. For 1 centimeter, how much potential difference is there? So now this current sensitivity is, that means sensitivity of potentiometer is inversely proportional to that. So to increase that, in order to increase the sensitivity of potentiometer, the resistance per unit length. That means how it is inversely proportional to sensitivity means you can consider simply this equation here. We know already in the galvanometer we discussed already, current sensitivity is inversely proportional to this current, because current sensitivity is defined as deflection per unit current, right? Theta by I we mentioned there in galvanometer discussion. So then so it is inversely proportional to this I here. Sensitivity is inversely proportional to I, and now this I is inversely proportional to R we can write here, and so that sensitivity is directly proportional to R, or we can say that R is directly proportional to L and sensitivity is directly proportional to L we can write here. And now this and from here only we are saying that it is inversely proportional to the potential gradient here, because now this sensitivity we can write this as So sensitivity is directly inversely proportional to this IR we can write here. So that means now this IR per L is nothing but we called a gradient here. So this value is nothing but we mentioned it as a gradient. So that means now we can call this as inversely proportional to the gradient here. So that is why we are writing like inversely proportional to the gradient. So it depends on the resistance in the primary circuit. It depends on the resistance in the primary circuit. So what is mentioned here? So in order to increase the sensitivity of potentiometer, resistance in the primary circuit is to be decreased. So resistance in the primary circuit, if you are decreasing that, then sensitivity value will be increased. So that is nothing but what we are saying here. So it is potential gradient will decrease. When potential gradient is decreasing, then automatically the sensitivity of that circuit will increase there, right? And so then length of the potentiometer has to be increased in order to increase this more accuracy. That means now you can observe that this potential drop per unit length means then this L is nothing but actually this length of this potentiometer wire here, capital L. So this L will goes to the numerator there from this expression if you want to say. So then current sensitivity is directly proportional to the length we can write here. So current sensitivity is directly proportional to the length. If you are increasing this current sensitivity, then automatically this length of this potentiometer, if you are increasing this length of this potentiometer wire, then automatically current sensitivity also increases, right? So that means that is the dependence on current sensitivity and length. And actually here in this expression, while we are discussing about this potentiometer, principle of this potentiometer, here also remember this one point here. So sometimes they will give the problem like by keeping all the data in remains constant in this primary circuit, they will change only this length of this wire here. The length of the total length of the wire in the potentiometer will be increased by keeping all the cells and all the resistors remains constant in the circuit. Then only these two are changed. So mention that note also here. If potentiometer length is increased by keeping all the parameters remains constant. That means only length of the potentiometer wire is increased by keeping all the parameters including the cell in primary circuit, cell in secondary circuit and all the resistors remains constant, then what we can write is this small l by capital L will be a constant value. This ratio will be a constant value. You can observe this. We are keeping all the parameters constant here except this small l and a capital L. Even this EMF of the cell in the secondary circuit is also constant. So that means then what we can write is L by L is constant here. Or I can write this L is balancing length is directly proportional to the length of this potentiometer wire. So this is remember this is valid only when remaining all quantities remains constant. There will be problems based on that. So initially length of potentiometer wire is say 10 meters, now it is increased to 11 meters. What will be the new balancing length they will ask? Simply you need to use this relation there, right? And so now let us see this comparison of EMF of the cells here. So for the comparison of EMF of the cells, generally the circuit will be shown like this. So this is a potentiometer and this part is nothing but we call the primary circuit here. So this part is primary circuit and this is a secondary circuit here. So here we are connecting the two cells E1 and E2 whose EMF is to be compared here. So we need to compare the EMF of those two cells there. So E1 and E2 EMFs, E1 and E2 EMFs we are comparing here. So for that these two cells are connected by using a two-way key. So this is called a two-way key, a high resistance box jockey. Instead of a single cell in the previous principle in the previous discussion, now we are connecting the two cells by using a two-way key. So then this is the circuit here. And so now let us see this the devices required here, materials required for this. So ammeter, a digital ammeter we are taking here, and this is the one-way key, and this is the rheostat here which we discussed already, and this is the battery in the primary circuit, and these are the two potentiometer with this wire and scale connection. This is a one cell Daniel cell we are taking here, this is a latch cell, and this is another cell we are taking. Just two cells we need to cancel. This is a two-way key, high resistance box, and this is a galvanometer here. So a galvanometer is connected, that means galvanometer here. So let us see the procedure now actually here. So now we are connecting the circuit here. The one terminal of this negative battery is connected to the one end of the potentiometer, other end is connected to the key, and then it is ammeter in series, and it is in series with the rheostat. Next we are connecting two cells to this common point where the positive terminal is connected here, right? So you can observe that The positive terminal is of the primary circuit is connected here, and this positive terminal of these two cells are also connected to the same point. Now these two cells are connected to the two-way key, and then that is connected to the high resistance box, and then galvanometer and a jockey in series with it, right? So these are circuit connections for that. And so next we keep some plug. We are closing the key in the primary circuit, and we adjust this jockey here so that we can put any desired value in the resistance and desired current in that circuit there. Then we are using the two-way plug key here. So this is nothing but our two-way plug. If you close this, then this circuit will be closed here. That means this cell will be included. If you are keeping this knob here, if you are closing this, then this cell will be included here. So that means at a time only one cell will be included in that circuit there. So at a time only one cell will be included in that circuit. So you can observe that clearly here. If you are closing here, then this will be the conducting path available. If you are keeping this knob here, then this will be the conducting path available there. So next, so then we adjust the jockey here. That means we observe the deflections in the galvanometer here. So then we are pressing the jockey at the different wires here. Here a series wires are there, as we discussed. Nearly 10 meters wire will be there. So 10 wires will be there. So we are pressing this jockey and we are observing the deflection here. So observe this here. So observe this slide here. We are pressing it at different points here. Now observe the deflections in this galvanometer. So I will show again it. So this is first second wire we are measuring here, and then see this. So we are pressing the jockey at the fourth wire, then we are getting the deflection on the left side. Then we are pressing at the sixth wire, then we are getting the deflection still on the left side. Then we are pressing at the eighth wire, then deflection is in right side. So that means in opposite direction. So that means that zero deflection. Now you can observe that from 6th to 8th where if you are moving, then deflection is in opposite direction. That means current is flowing in opposite direction. So null deflection will be there between the 6 and 8 here. So at the 7th, between 6 and 8, we need to observe it carefully here, where you will get that zero reading there. So that means now this is the 8th wire. Now jockey is pressed at that point, 6th wire and 8th wire. It is showing in deflections in opposite direction. Then so we are verifying here between 6 and 8. Now we need to verify carefully. So until this galvanometer shows zero reading. When it shows zero reading, then we measure this balancing length like this. Like for example, we are taking it as some 7.11. It is an example only. And so now here we balancing. That means that the table column will be like this. Now meter reading and even balancing length when first cell is connected and then second cell is connected. We write the ratio here. Next we change the ammeter reading. And then again we repeat the process. Then again we find the balancing length by using first cell and balancing length by using second cell. Then we find the ratio here. So then we repeat. That means we change the knob here so that now this cell is now included. Then we repeat the process here. So we repeat the process until this galvanometer shows a zero deflection here. So at some point it will show a zero deflection. Then we note that value as L2. So then this is our balancing length here. So then according to our principle, when all remains constant, when all the parameters remains constant, E is directly proportional to L. So that we can write here E1 by E2 is equal to L1 by L2. So EMF of the cell is directly proportional to that balancing length, which is the principle of this potentiometer. So from that we are writing this as E1 by E2 is equal to L1 by L2 here. So this is experimental procedure. So next we change the ammeter reading and then we repeat this process here and we take 4 or 5 readings and then so here observe this. Now we are taking 0.42 milliamperes. Then we are again repeating this by for E1 and E2 we are finding the balancing length for the different current and another current here and we find the finally average values there. So we are finding balancing length for E1. So that is for 42 milliamperes, then E1 balancing length we are getting. Then again for E2 also balancing length we will find here. As we are increasing the current, then automatically balancing length will decrease because more potential difference will be there across this wire. So again we are finding this value, balancing length. So 9.31 meters we are getting here. So then less than the previous value, then we are getting another value like this, E1 by E2 value. So like that we repeat this experiment here. We repeat the experiment for 3 or 4 values, and then we find this finally the average E by L1 by L2 value, that means average E1 by E2 values we can find there. So it is a generally procedure for this. So that means then this is again for another current E1 and then E2 values we can find here. Then we find the finally this average values there, right? So it is a comparison of EMF of the cells. So comparison of EMF of the cells means we need to write that E1 by E2 is equal to L1 by L2 values we need to write here. So this is a comparison of the EMF of the cells as we discussed now. So just this E1 is a balancing length for this L1. L1 is a balancing length when the cell E1 is connected in the primary circuit, and L2 is a balancing length when the cell E2 is connected in this. So this is a two-way key what I shown now. So that means by connecting here, then this E1 is connected in the circuit, then E2 is excluded from the circuit here. Then if you are changing this key from here to here, then E2 will be included in the circuit here. So that if E1 and L1 and L2 are the balancing length, respective balancing length, by using our principle of potentiometer, which is nothing but E is directly proportional to L, we can write E1 by E2 is equal to L1 by L2, we can write that. So it is a comparison of EMF of the two cells. And next this determination of internal resistance of the cell will be there. And so now see this, I will explain that, and after that I will show this animation required for this. So this is a circuit diagram for this, and here let us wait a minute, and here actually this one more method will be there for this comparison of EMF of the cells here. So this is when the cells are connected directly here. So sometimes in the secondary circuit the two cells may be connected like this. So that means now the two cells may be connected in series like this. This is say E1 and E2. That means now both the cells are used at a time. Both the cells are used at a time in the secondary circuit here. Then this galvanometer and then remaining connections will be there here. Jockey connection will be there, so that this circuit across this potentiometer wire we find the balancing length as we discussed there, right? And so now if suppose if you are using two cells like E1 and E2 at a time like this, then this is balancing length is L1 for example. Then what we can write is this E1 plus E2 is directly proportional to L1 we can write. We are using two cells at a time. Previously we used one cell and then another cell separately there. We are connecting those two cells separately. So that means here we may mention that as a continuation of previous discussion, like comparison of EMF of the cells. Mention this as when both the cells are used at a time. At this point we need to consider let L1 be the balancing length when both the cells support each other. So both the cells support each other means then both the EMFs are connected in the same direction, or we can say that they are connected in series. And the another condition is like when the cells are connected like they are opposing each other. So they are opposing each other means they are connected like wrongly connected cells. E1 and E2, they are like wrongly connected cells. So when they are wrongly connected, then EMFs, their EMFs will oppose there. Then suppose L2 is the balancing length. So let L2 be the balancing length when their EMFs are opposing each other. Then what we can write is E1 minus E2 is directly proportional to L2 we can write here. So then you can take the ratio of these two equations here. So take the ratio of these two equations, then we can write like E1 plus E2 by E1 minus E2 is equal to, I can write this as L1 by L2. And our required value is we need to find this E1 by E2 from this, right? So if I write this E1 by E2, then I can write this as L1 plus L2 by L1 minus L2 we can write. So this is the EMF of the cells when both the cells are connected at a time. If they are connected separately, then directly we will get like E1 by E2. So you need to remember, sometimes they will give the problems like this. So this they will mention this as when the cells aid each other, when the cells support each other, or when the cells aid, AID. And when the cells are opposing each other, then you will get E1 minus E2 as this EMFs here. And now let us come back to this internal resistance, determination of internal resistance of the cell here. So this is a simple as we discussed in the primary circuit discussion. Now this is similar to that of that. Now additionally the difference in the circuit arrangement is here we connect some resistance here. So we connect some resistance across the cell here or in parallel with the cell through this another plug key here. So let it be K dash. Here we are using already this K, so I am taking this as K dash here. So initially our procedure is, that is the only difference here. If you want to find the internal resistance of a cell, that cell, sorry, that cell is connected in this primary circuit, secondary circuit, and across this a known resistance is to be connected across this here and with the plug key. So initially this key is open, so that this resistance is excluded from the circuit. It is not included in the circuit. Then we plus the jockey at the different points and we find the balancing point, balancing length here. Then suppose it is L1. Then we can write this EMF of the cell must be equal to potential difference across this, because no current is flowing to this cell. So I can write this as E is equal to KL1 we can write. And next we close this key here, so that this resistance is also included in the circuit. Then we find after closing that the important thing you should observe here is there is some current flowing in this loop here, 1, 2, 3, 4. So across this we press the, after closing this again our procedure is same. We press the jockey at different points until you will get some zero deflection. Suppose at say some length L2 we will get the zero deflection here. So at L2 there is no current flowing to the galvanometer. So observe this carefully. Only there is no current flowing to the galvanometer, but still there is some current flowing in this circuit like this. So which I mentioned here as I dash here. So that I dash will flow only through this 1, 2, 3, 4 here. So that current, because it is a closed loop here, so current will flow through this closed loop here. And so now that I dash value we are writing here. The current in this secondary is in this small circuit we can write as E by, this is resistance, suppose say R, then R plus small r we need to write here. So then R plus R we are writing. So now the potential difference across that R is nothing but we can write this as IR. So then I dash here, I means that is nothing but I dash. So then E by R into, this is again capital E here, EMF of cell in the second, this same value, I dash value we need to substitute there. So then I dash by R plus R into R we are writing here. This potential difference must be equal to potential difference across that length L2, across that potentiometer wire. So then this value is equal to then K into L2 we are writing here. Then this E value we can substitute this as KL1. KL1 E value we are replacing that KL1, and then from this we can simplify this. This K value will be cancelled, and from this we can simplify this as R is equal to L1 minus L2 by L2. So this is the expression for this internal resistance. So by using this expression we can calculate the internal resistance of this given cell. So here by using this only we need to find this L1 and L2 values to find the internal resistance. So L1 means, note this value clearly here, L1 means L1, where L1 is balancing length before connecting the resistance, right, before connecting the resistance, and L2 value is balancing length after connecting this resistance, right. And important thing here is L1 does not depend on the resistance, this R value, how much resistance you are connecting, this L1 does not depend on the capital R. And actually this smaller internal resistance of the cell, can you say internal resistance of the cell, if you are changing this small r value, capital R value, that means the resistance connected across this, if you are changing this capital R value, is there any change in this internal resistance of this wire? Can you guess? Is there any change if you are changing this R value? There is no change, because this is the internal resistance of the cell, which is the property of the cell. So that means we discussed already on what factors this internal resistance of the cell depends. It depends on the nature of electrolyte and the size of the cell and the concentration of the electrolyte, and it depends on the temperature, but it does not depend on how much resistance, external resistance you are connecting there. So it is the property of the cell, it does not depend on any external factor, external parameters there. So like that means here this small r value actually does not depend on either L1 or L2 or R here, right. So actually these values will depend on this R, how much resistance is there, that those values will depend on that. So again I am saying L1 value does not depend on this R value, and again this R value, capital R value, and this small r value, internal resistance of the cell, does not depend on L1, it does not depend on L2, and it does not depend on R. We discussed already, we mentioned already the EMFs and internal resistance, so it depends on only those parameters there, right. So it is the internal resistance of the cell. Now I will show this just an experimental procedure how to find this internal resistance. So now let us see the experimental procedure for determining this internal resistance of the cell. So as we discussed, this is a circuit diagram for this. So this is a circuit diagram, this is a potentiometer, and this is a cell and a external resistance we are connecting here. So then across that by using a key. So now let us see the materials required for this. So then one-way key and rheostat, digital ammeter, battery. This is a battery, primary circuit, and this is a potentiometer, a resistance box, and this is a another cell, Lecture cell, and this is a one-way key, and this is another high resistance box in series with the galvanometer, and this is a galvanometer here, right? And so now let us see the procedure for this. So then here observe this procedure, experimental procedure here. So that means here we are making the connection so that you can observe here, you can compare with our circuit diagram there here. So we are connecting positive terminal of battery is here. So that means one end is connected to this primary potentiometer here. The another end is connected to the key. So observe this. So it is blinking here. And then it is connected to the ammeter. And then it is connected to the rheostat. And the other end is connected to the potentiometer. So this end is connected to the potentiometer. And the other end is connected to the resistance box. And this is key. Key is connected to the cell. And a high resistance box. The cell is connected to the high resistance box, galvanometer, and then jockey. So that is a arrangement of the circuit here. Now let us see the experimental procedure. So we are closing this key here. So let us close key and adjust this rheostat here so that you will get some desired current there. Desired current is obtained in that. And we check the connections in that galvanometer and then start taking these readings here. So then again we are pressing at some points here where the current deflections are in opposite direction. So from that we can start measuring this balancing length there as we discussed in the comparison of EMF of the cells. So for 1, 2 and that is in the same direction here. So as you can observe here, as we discussed in the previous comparison, for 4 it is left side and 6 also left side, and for 8 it is right side here. Always it need not be like that. Sometimes you may get the opposite direction for 4 and 6 also. That depends on those values, resistance values and the currents what we are taking there, right? So it is an example only. So then current you will get for 6 and 8 we are getting opposite direction, means then balancing length will be there between 6 and 8 only. So then slowly we measure more carefully, we measure between the 6 and 8. So further we measure at the ends directly, and where we observe that where you are getting the opposite deflections in the opposite directions there. So we measure carefully between 6 and 8, and where this galvanometer shows a 0 reading. Between 6 and 8 only that balancing length will be there. Suppose if you are getting some like balancing length somewhere here on the 7th wire, for example, if you are getting, then we measure the balancing, we note the balancing length for this. So 7.83 meters for example we are taking. This is again example only. So then the table will be like this. So then table will be shunt resistance, how much we are connecting here across the cell. And then without shunt, first we are finding the balancing length. Next, by including the external resistance, we find the balancing length. Then by using this, we find the resistance, internal resistance. Then again for the experimental procedure, again we change this shunt resistance. We increase the shunt resistance there. Again we find the balancing length without connecting that resistance, and after connecting that resistance, and again we find these values. And finally we take the average values here. That is the procedure. So now this is without shunt, we are finding this value. Next we include some resistance here. For example, 0.2 ohms we are placing here. 0.2 ohms. So that's value we are removing, means we are including that resistance. Then this display key is closed here so that this resistance is included. Then again our procedure is same. We press the jockey at the different points until we get the 0 deflections there. So then for example here we are getting the 0 deflection here. Let us say 59 centimeters. So then we are taking that as balancing length as 59 centimeters when the shunt resistance is included. Then we find the internal resistance. Then again we repeat the experiment here. That means we change this resistance here, external resistance. Then that means shunt resistance. Then we repeat the experiment here. So we repeat that experiment, and finally we find the average internal resistance there. That is experimental procedure of finding this resistance there. So again we are finding this resistance, and that means balancing length after changing that resistance. Say for example 31 centimeters, sorry 1.31 centimeters we are getting here. So that means this value we need to change. Now we can observe that even though we are changing the shunt resistance, without shunt resistance L1 value will remain same. We are taking the same value here because it doesn't depend on this resistance here. Only this L2 value will changes, and correspondingly this balance corresponding internal resistance we are finding here. Here we are getting the small difference because of experimental errors, and because of that only we are repeating these values here, and finally we find this average value of that internal resistance. So that is a procedure for finding the internal resistance of the cell, right? So that is the uses of this potentiometer here. So we can find the potentiometer, we can use the potentiometer for finding this EMF of the cells, or we can compare the EMF of the cells, and we can find internal resistance of the cell, and we can use to calibrate any voltmeter. And actually with the help of this we can also find the resistance, and that we will discuss in the numericals. So that means we can find the potential difference across any part of the circuit, and then from that so any part of the circuit, and with the help of that we can find this in resistance of the circuits also. That means resistance of the given resistor also we can calculate. Actually resistance we discussed by using this meter bridge. So here also we can calculate the resistance with the help of this potentiometer calculations. So the problems based on the potentiometer are completely formula based problems will be there. Most of the problems will be formula based problems will be there, either based on meter bridge or the potentiometer. So all these meter problems are very easy problems. So majority of them based on the formula only. So you need to understand the concepts carefully. And again I am saying, after listening this class, read the potentiometer experimental procedure carefully in the textbook, so that you will get an idea about that. So if you are understanding that procedure and understanding about this experiment, you can solve the problems very easily, because all those problems are based on this formula only. And in the tomorrow class I will explain the problems based on this potentiometer there, right? So thank you.